Swayam Prabha. Digital India. Educated India.
Welcome to module 6 lecture 29. Today I will discuss about the different electrochemical testings. Those are used for the characterization of electrochemical properties as well as to some extent chemical properties of the surface. So, if you just quickly go through the electrochemical testings, you will find that these all electrochemical testings are basically applied to know the corrosion behavior of different modes of corrosion. So, particularly aqueous corrosion. So, if you just quickly think of the aqueous corrosion and its classification, you will find that aqueous corrosion may broadly be classified into 8 categories like general corrosion, pitting corrosion, crevice corrosion, intergranular corrosion, selective leaching, and then stress corrosion cracking, hydrogen embrittlement, and so forth. And you will find that each and every corrosion sub corrosions, or maybe you can say subdivisions of the aqueous corrosion is having its own identity, and also they are also just evaluated in a different way, and it is very important to know how each and every aqueous corrosion mode of aqueous corrosion is evaluated with the help of electrochemical testing. In this regard, I would like to state that you could also evaluate this particular corrosion by chemical testing, but actually if you would like to do that in chemical environment, in the simulated environment, you have to wait for a long time, and those all processes are quite lengthy in nature. Obviously, to some extent where your component is highly expensive and it is applied for strategic purpose, it is procured for, maybe it is fabricated for strategic application, there you have to follow that typical field test, which is the mandatory, but otherwise in all other cases where that routine test is required, where you are interested to know the corrosion behavior in a particular solution or in a particular media where media is known to you, there you can do this electrochemical testing, which is highly accelerated testing in nature, and where you just apply impressed voltage, and then subsequently you just try to find out behavior of the corrosion behavior of the component electrochemically by knowing the current density. And like that also there are several other testing procedures are there. Sometimes you apply DC current, sometimes you apply AC current. So, depending on the kind of current you are applying, different names are also there, but those are very much important and routine and highly documented in the textbook, or maybe you can say that metal handbook. Now, in addition to the electrochemical testing which we will be discussing today, I also need to mention that corrosion, it may broadly be classified into 2 categories. One is aqueous corrosion, another one is high temperature oxidation, or maybe you can say that another type of corrosion is also hot corrosion. So, if you would like to measure or evaluate the high temperature oxidation resistance property of any component, there you have to go for 2 different important testings, like you have to go for oxidation resistance testing in for example, isothermal way or maybe in cyclic way. So, these 2 testings are also can be carried out either in furnace where tube furnace, where you can control the environment. So, where you do is basically you go on applying the, you go on passing the oxygen at a regular or at a periodic, I mean you can say that at a constant rate, where flow rate can be changed, and you change the oxygen partial pressure, and subsequently you just go on doing the isothermal testing or isothermal oxidation testing by keeping the component in a particular temperature for at regular interval, and subsequently measuring the weight gain of the component as a function of oxygen partial pressure, temperature and time. So, if you know that this particular weight gain or weight change of the component as a function of like time and temperature, then you will be able to know the activation energy of the oxidation. Certainly there you will find that as you go on changing the alloy composition or as you go on changing the surface composition, the activation energy of the oxidation will also change. So, if you just quickly go through the isothermal oxidation of material of any component by either modification of the surface or without modification of the surface, and you will subsequently compare them, you will be able to understand that how is the behavior and whether any surface treatment which has already been applied on the surface is effective in enhancing the oxidation resistance property of the component. You can also carry out other kind of oxidation test, that is called cyclic oxidation. So, in cyclic oxidation test, what you do is that you just go on applying the cyclic heating of the component in a particular environment. Like if you are interested to know the cyclic oxidation behavior of any metal in or maybe alloy in oxygen environment, there what you have to do is that you have to fix the cycle, and that cycle depends on the application of the component. For example, if the component is for aerospace nozzle, or maybe if the component is for like any marine applications at high temperatures, that engine nozzles, and there you have to know exactly the kind of cycle the component is subjected to. So, as per the cycle, for example, if you see that heating cycle is for 10 minutes, it is heated up to 1000 degree Celsius, then it is cooled quickly, very quickly at a rate of 1 degree Celsius per minute, and then again it remains there for 2 minutes, and then again it is heated at a specified rate up to 1000 degree Celsius. So, if the cycle is known to you, so you do similar cycle in the similar heating and cooling cycle in the normal your environment. So, that in that environment you can have the high temperature furnace where you just go on passing the gas flow whatever is there in the simulated condition, and you heat at a specified rate and then cool it and then keep it for a certain period of time, then again heat it for a specified rate, cool it and keep it for a certain period of time, and after each cycle you measure the weight change of the component, and subsequently what you do is that you just go on plotting the weight change per unit area as a function of time for different temperatures, and from there you get the information about rate constant. And if you just go on observing the variation of rate constant with temperature, and you just go on measuring that particular things and subsequently plot the Arrhenius plot, then from there you can get the information about the activation energy of cyclic oxidation. So, for oxidation resistance property, these two tests are very much common and very much popular and well established. If you are interested to know the hot corrosion behavior of the component in a specified environment, for example, if you are interested to know the hot corrosion behavior of the component in the mixture of sodium chloride and vanadium sulphate. So, in that case you just mix up these two salts properly and then keep the component within that salt mixture and then heat it up at a particular temperature of your interest for a certain period of time, and after every period of time you just go on observing you clean the surface, measure the weight change, and subsequently you also observe the surface by electron microscopy, and by that process what you do is that every time if you go on doing these things you will find that how component changes its structure as well as how the component changes its, I mean you can say that loses its matrix from its surface. So, because of the hot corrosion again there will be some loss of material. So, that loss of material you record as a function of temperature and time, and you also observe the surface condition of the component as a function of time and temperature. So, this is how you just go on evaluate the hot corrosion behavior of any component of your interest. So, these are about high temperature oxidation and hot corrosion testing of the component. Now, I would like to say a few tests which are applied for knowing the electrochemical corrosion behavior of the component in aqueous solution. So, one of the important testing or very widely used technique for corrosion testing of the component in a aqueous environment is potentiostatic polarization technique. So, what you do is that you polarize the component. You in this particular test you electrode you basically you use 3 electrode systems, where your working electrode is kept in between the counter electrode and that of reference electrode. Reference electrode you can use standard AgCl as well as standard calomel electrode. So, this electrode is reference electrode, and counter electrode you can use platinum as counter electrode, and your component is actually in between. So, you just go on applying the, you just keep it for a while so that the component surface remains in steady state with the remains in equilibrium with the solution. Your solution may be anything of your interest. If you are interested to know the corrosion behavior in sulfuric acid solution, for example, 1 more sulfuric acid solution, then you take 1 more sulfuric acid as the electrolyte. If you are interested to carry out corrosion behavior of the component in 0.5% NaCl 0.5% HNO3 solution, or maybe 3 to 4% sodium chloride solution, this standard solution you take, and then you basically go on apply the voltage which is little bit nobler to that of the equilibrium voltage. So, a little higher than that of that standard open circuit potential of the component, and then you just go on passing electrical current. You will find that you go on applying the voltage. For example, you can change the voltage from a value a little bit active of that of OCP to that of much nobler to that of OCP. Then you will find that it will follow this kind of diagram. So, whenever it is a little active or maybe lower than that of OCP value, there you will not get any corrosion, but on the other hand, whenever it is higher than OCP value, you will find that there would be corrosion. And from the typical, this is typical Tafels plot. So, from the Tafels extrapolation, you can easily calculate the corrosion behavior of the material. So, actually this is the typical corrosion rate, which is which the equation of which can be used for the measurement of the corrosion rate if you know the I core value, and also equivalent weight and density of the component is known to you. So, these all behave, this is very interesting and quick way of measurement of the corrosion rate as a function of any kind of solution as well as any temperature. You can also change the temperature and find out the activation energy of the corrosion. And certainly, this is not the only test. You can also go on having similar kind of test to a different extent, like to a different level, like you can find out at a particular E value or applied potential higher than that of that OCP value. You can see how the component is corroded if you just measure the E value as a function of if you just measure the I core value as a function of time. So, you will find that if the materials usually what happens is that whenever corrosion starts, there is formation of very thin oxide film. Whenever if you just if the oxide film is highly protective in nature, then you will find that as soon as the surface is covered with the oxide film, there would be any corrosion. But on the other hand, if the oxide film which is forming on the surface is highly porous in nature, if it is not protective, then you will find that as the component is kept in that solution, gradually there would be loss of material because of the corrosion, and that particular loss of material or corrosion process is basically it is reflected from the I core value or maybe corrosion current which is flowing within the which is flowing through the component. So, you just record the corrosion value as a function of time at a fixed applied potential. From there you get information about the protectiveness of the film. So, like that with a simple test you can have lot of information about the mechanism of corrosion. Particularly this is highly effective test for the newer kind of component if you develop, and you can get many informations which are highly basic in nature and which is having very high value in terms of understanding the mechanism as well as to clear the fundamental idea about the corrosion process in this particular technique. This is a very simple technique. So, now if you just quickly go through the active I mean the metal which does not undergo any passivation, there you get this kind of behavior, and here there what happens is that corrosion current goes on increasing with increase in applied voltage. But on the other hand, if you take the kind of metal which basically forms a passive layer on the surface, like the case for the stainless steel. So, AISI 304 stainless steel or titanium, you will find that as soon as the surface is covered with the oxide film, there is that the surface gets passivated. Passivated means it becomes highly neutral, or it is the scale becomes highly protective in that environment. So, you will see that immediately after this particular primary passive potential, the corrosion rate decreases to a large extent, to several orders of magnitude, because surface is highly protective. So, it is corrosion film forms and the surface is no more active. So, it becomes passive in nature. Then as you go on increasing the potential, then you will find that after a while you will find that gradually as the potential increases the threshold value, then the passive film it basically breaks. So, then because of the breakage of the passive film, again you will find that that is again a kind of severe aggravated condition which leads to initiation of the pitting corrosion. So, where you will find that if the passive region discontinuously breaks somewhere, you will see that again there will be unfavorable area ratio, that is very low anode to cathode ratio, because where it is breaking discontinuously, there you will see fresh surface is exposed to. On the other hand, surrounding area is basically it is full of the passive film, that is in case of stainless steel it is chromium oxide film. So, at that potential there is breakdown of the passive film. So, you will find that there is increase in the current density at a much rapid rate. So, that is called transpassive region. So, naturally you will find that whole film breaks. Again if you see that fresh surface is exposed to, then again there may be secondary passivation behavior, where again there is passive film formation. Then certainly after a certain period of time you will find that when the E value increases to a large extent, there will be oxygen evolution. So, that is the case where the component stops or maybe you cannot use the component at all. So, usually what happens is that in electrochemical testing, the applied potential is equivalent to that of aggressiveness of the environment. So, if you would like to state that property of that particular component in a specific environment, safe environment would be the potential in the passive region. So, if you just keep the component within this passive region, or if the aggressiveness of the environment is within the passive region, naturally you will see that there will not be any corrosion at all, and that is the safe region for the operation of the component. So, in this particular, if you are interested to know the corrosion testing by typical potentiodynamic polarization testing, you have to go on several steps actually. So, first step is surface has to be highly cleaned and also should be defect free, and then you have to measure the surface area, because corrosion rate is depends on the corrosion, basically overall corrosion what the component is undergoing, it depends on the exposed surface area. So, in that case you will find that if you go on increasing the exposed surface area, corrosion actually increases, but you have to normalize that thing. So, actually corrosion rate is actually represented in terms of corrosion plus corrosion rate, or maybe you can say that this is that is current flowing divided by the surface area, or maybe current density, or maybe you can say that corrosion per unit area. So, you have to measure the surface area, and then you have to go on cleaning the surface, then weighing the surface, then you have to go for masking if needed. If you are interested to know the corrosion resistance or corrosion behavior of the localized part of the component, you have to go for masking, then you have to go for exposure, and then if you have to inspect the specimen after exposure and determine the. So, this is the way actually then determination of corrosion rate. You can either apply the electrochemical technique by potentiodynamic polarization or with the help of by applying potential with the help of potentiostat, or otherwise you can also do that by simple field testing or coupon testing process, where you expose and subsequently do chemical testing. But mandatory requirement is that you have to clean the surface properly and do all the follow all the steps essential for the corrosion testing prior to corrosion testing. Now, as I said you that the aqueous corrosion may broadly be classified into 8 categories. So, first of the important or very simple category of corrosion is a uniform corrosion, or you can say that environmental corrosion, where corrosion is uniform all throughout the surface. So, there you have to you can use the typical these potentials with the help of potentiostat, you can apply electrochemical testing, or otherwise you can also apply simple mass loss testing or standard coupon testing, where you keep the component in the given environment for a specified period of time and you try to calculate or record the just mass loss or mass gain per unit area, and finally you just do the testing for an average period of 1 month or 2 months or maybe 5 months. If the component, if the environment is changes, if you would like to see the variation of the environmental fluctuations on the corrosion rate, then that case what you do is that you keep it in the environment for a period of 1 year or 2 years, where you see that all environmental fluctuations are taken care of, and then you just establish the corrosion rate in terms of average corrosion rate, that rate of materials loss per unit area, in terms of rate of materials loss per unit area per unit time. So, now coming to the this name of the this particular test, what I discussed is ASTM G59. So, this is a typical ASTM standard. So, now another testing standard, if you are interested to know pitting and crevice corrosion behavior of any component, you have to apply ASTM G48 standard. So, where in this particular testing you can know the pitting corrosion behavior and also crevice corrosion behavior of stainless steel and relative alloys, or whatever alloys, any alloy which undergoes pitting. Usually we saw that the alloys which undergoes pitting, they are those alloys which have the tendency for passivation. So, what is said, when it is exposed to an oxidizing chloride environment, usually you can use 6% ferric chloride at a particular temperature, or otherwise you can also use 5% sodium chloride solution or maybe 3.56% sodium chloride solution. So, there what you go on doing is that if you just go on measuring the typical standard coupon testing, if you just go on you go on estimating the pitting corrosion behavior by typical standard immersion testing technique, there you basically immerse the component in the solution and just try to find out the surface condition at regular interval, so that and measure the area fraction of the pits which formed on the surface. So, this is called standard coupon testing. So, where unless and until you understand that when we discussed about pitting and crevice corrosion, particularly pitting corrosion, we saw that pitting corrosion, if you would like to know the pitting corrosion rate by measuring the weight change of the component as a function of time, you will see that weight change is not really significant in pitting corrosion, but problem is the propagation of the pit. So, what is important here is that in pitting corrosion, so if you just go on measuring either electrochemically or chemically the weight loss because of the pitting corrosion, you will see that it will misguide you. It won't give the exact aggressiveness of that particular situation, or maybe how aggressive the solution is to cause the corrosion. So, what is mandatory there? Mandatory requirement is that you observe the surface and find out how many pits are forming on the surface, or maybe what is the volume of the pits that are forming on the surface as a function of the time of the exposure. So, on the other hand, if you would like to measure it by electrochemically, there you just try to find out that potential for peat initiation as well as potential for the peat propagation, critical potential for peat initiation or critical potential of the peat corrosion. So, there are different methods for measuring the peat corrosion, like method A use ferric chloride pitting test, and then method B ferric chloride crevice test, method C PT critical potential temperature test for nickel based chromium bearing alloy, method D critical crevice temperature test for nickel based chromium bearing alloy, then method D is a critical pitting temperature test for stainless steel, method E critical crevice temperature test for stainless steels. So, there are different ASTM standards which are noted here. So, like ASTM F746, it gives you the procedure to determine the resistance to pitting or crevice corrosion for passive metals for the surgical implant applications, and G61 gives the electrochemical test method for. So, this was I was saying that if you just go on doing the electrochemical testing and find out the typical pitting corrosion behavior. So, there the kind of behavior which you get is like this. So, what you do is that there you do cyclic polarization test. So, if the solution is usually that sodium chloride contains any chloride species, you will find that this typical passive region is missing over there, because if you take 304 stainless steel and if the environment is chloride, environment contains chloride. So, in this particular solution the passive film gets damaged. So, you will not get any protective behavior. What you get is that you immediately after the typical these things critical at primary passivation potential, you will see that the passive film remains, but there is not much change in the corrosion current density. So, the behavior is like this, then after that it remains and then there is peat propagation. So, it is called peat initiation and not really peat initiation, you can say that primary passivation potential, and this particular potential is called actually the peat initiation, critical potential for peat initiation. Now, if you are interested to know the potential at which the peat will start propagating, you have to go for cyclic polarization test. So, in that case what you do is that in cyclic polarization test what you do is that you just go on initially applying the that forward potential, then you just go on applying the backward potential, I mean you go on doing reverse polarization testing. So, in that case the kind of behavior which you will observe is like that. Initially there is increase in current with increase in potential, then at a particular primary passivation potential there is passivation, passive film formation. So, current does not change with the you will see that current does not change with the potential up to a particular potential. Then again at a threshold potential you will find that there is peat initiation, and as a result of which the current density increases at a much rapid rate with a little change in voltage. So, on the other hand, if you do reverse polarization, what would happen is that it will follow this typical kind of curve. So, if the peat propagation is completely if you see that peat propagation is really not there in that sample or in that component, in that case the critical potential peat propagation will be much nobler than that of that OCP or open circuit potential. Or on the other hand, if you see that critical potential for peat propagation is much active than that of typical that pitting potential or open circuit potential, you will see that usually there is propagation is usually propagation is always there. So, this kind of behavior you can always this kind of quantitative information you can always get from the critical potential of peat formation or critical potential for peat propagation. So, higher nobler is the critical potential for creep initiation, the higher is the or maybe you can say the higher is the resistance of the component to peat initiation. On the other hand, nobler is the critical potential for peat propagation. So, higher is the resistance to peat propagation. So, that EP1 and EP2, these are two important values from where you get information about the peating potential, that peating tendency you can say. So, ASTM G100 gives a procedure for conducting cyclic galvanous staircase polarization to determine the relative susceptibility to peating corrosion of the alloys. Here the current is increased and decreased and potential is monitored. So, this is typical test which you can again carry out using that this potentiostat, and it gives more reproducible protection potential value as compared to that of potentiodynamic method as in shown in ASTM G61. So, now this is typical case where you will see that typical magnesium based alloy MEZ where surface has been refined by laser melting. So, if you see this kind of any material which shows this kind of grain boundary precipitations, they are very prone to or susceptible to intergranular corrosion. So, the magnesium, this alloy is also very much susceptible to intergranular corrosion. So, what was there is that we tried to do laser melting and subsequently make it highly refined. What happened is that this particular grain boundary precipitates got dissolved, melted and subsequently redistributed to cause refinement of the microstructure, and then we measured the typical corrosion rate by standard coupon testing, where area fraction of pits are shown as a function of immersion time. So, what we found is that in case of this particular big grain structure, the area fraction of peat is much higher than that of small grain structure. So, in addition to that, you will see that there is also increase in the hardness value for this particular case because of refinement of the microstructure as well as homogenization of the structure by reprecipitations in an uniform fashion. So, we also found the weight loss as a function of applied potential. So, you will see that this is also possible, as I mentioned you, with the help of that potentiostat you can do any kind of testing as you wish. So, if you measure the weight loss as a function of applied potential, you are basically aggravating the environment by applying the potential, and subsequently you measure the weight loss, you see that weight loss is much lower in case of defined structure as compared to that of adhesive structure. So, naturally whenever you are interested to know the corrosion behavior a little bit in details, you have to understand the mechanism of the corrosion. So, this micro mechanism of corrosion needs a detailed understanding of the post corrosion microstructure and also phases. So, we saw that we found out the post corrosion microstructure, we found that in adhesive structure the corroded film which is forming, that is highly loose and porous in nature. On the other hand, because of the typical surface melting, we found that film is more or less quite uniform and it is not really, it is also very much strong in nature. So, because of the refinement of microstructure and formation of initiation and formation of the protective film all throughout. So, you can examine the pitting corrosion, as I said that pitting corrosion on the surface you measure the area fraction of pit. If you see the cross section, you will see that the pits are not growing in a same fashion, somewhere it is in a capillary like fashion, somewhere it is triangular fashion, somewhere it is zigzag fashion. So, in different fashion pitting grows. So, if you are interested to know exactly the pitting corrosion behavior or exactly the material loss due to pitting, you have to measure the overall volume of pitting. So, that is really very tedious job, because you have to take at least 1000 or 2000 points per square centimeter and per square you can say that square meter actually 1000 or 2000 points and across the surface, and then you have to know this typical pitting volume with the help of optical profilometer. You have to know do the surface profiling and subsequently see the volume of the material loss due to pitting. and then you have to take the average of, you have to do the average of the same. So, it is highly very much tedious job. So, better would be you try to establish the pitting corrosion resistance in terms of critical potential for pit formation and critical potential for pit growth. So, similarly for crevice corrosion you can go for ASTM G78. So, these all details are available in the ASTM handbook. So, you can refer this book to know the protocol those are followed for knowing the different types of corrosion testing, like ASTM G82 can be used for galvanic corrosion resistance measurement. Similarly, G71 it is practice for conducting and evaluating galvanic corrosion test in electrolyte. Similarly, for intergranular corrosion you can use ASTM A264. So, there are different practices. So, these practices are followed industrially. So, particularly whenever people are interested in industry to know the corrosion behavior of any component, they do follow these all practice in different solutions, and from there they find out the corrosion behavior in a detailed way. So, intergranular corrosion again in austenitic stainless steel, these are the different test procedures that are followed. So, due to paucity of time I am not reading these all things, it would be available in ASTM handbook. Also you can refer these all things which are noted over here. G34 is used for exfoliation corrosion measurement, corrosion testing, particularly for aluminum alloy. This particular corrosion is very much applicable. For knowing the stress corrosion cracking behavior, you have to go for ASTM G139, where the stress corrosion cracking measurement is a quite lengthy process. So, it requires lot of patience. So, and also time, usually 1 to 2 months time is required for knowing the stress corrosion cracking behavior of any component. So, these are the references which you can follow for knowing the different types of testing which are used for the measurement of aqueous corrosion behavior of any component. So, naturally in this particular talk we discussed about the different ways by which you can measure the aqueous corrosion and high temperature oxidation resistance property of any component, and in the next class we will be discussing about how to characterize the surface, particularly prior to corrosion testing and after corrosion testing. Thank you very much.